and spatiotemporal quantum reference frames.
Thank you. So my name is Michael. I'm a postdoc at Bar-Ilan University in Israel. And first of all, I want to thank the organizers for the opportunity to present my work here. So today's talk is based on a recent paper, which is current under revision. You can find the online version on archive. Okay, I'm going to start with a brief introduction of spatial and temporal quantum reference frames. Then I will show how these two concepts can be combined to what I call spatiotemporal quantum reference frames. I use the term spatiotemporal, not space-time, because we will deal with non-relativistic regime here, and will be mostly focused on the distribution of spatial and temporal degrees of freedom. So after defining the framework, I will present an example to show the influence between these distributions in different quantum reference frames. Then we'll talk about more general conclusions that we can make in this framework with regard to expectation values and uncertainties as they are seen from different perspectives. And then I'll summarize and talk about possible generalizations of this framework. So I want to start, before I start with my results, I want to start with the comparison between the known things and the result of this work. So in the case of spatial quantum reference frames only, for example, in the scene in paper by Giacomini, Castro, and Bruckner, there is some kind of symmetry. So for example, if you look at the first photo, you see that the A particle in C perspective is perfectly localized, and the particle C from A perspective will be also perfectly localized and positioned in opposite direction. So we see that there are two features that have some symmetry. So the shape is the same when we change perspective, and the position as well. And I will show you later that when you take, in addition to spatial degrees of freedom for each particle, for each quantum reference frame, in addition there is a temporal one. This picture is no longer exists, and you see that the position of particle B in a reference frame is not anti-symmetric when you switch reference frames, and the shape can also change. Okay. So, if you take n subsystems, we'll restrict to the case of n equals 3 in my talk. The total Hilbert space is tensor product, and since only relative distances have physical meaning, that means that the physical state should be invariant under translations. That means that total momentum acting on the physical state should give 0. That means that the kinematical state is redundant, and the way to get the physical state is by applying the constraint on the kinematical space, and that reduces the space to the physical subspace. And this kind of integrals have, in this case, 3 equivalent forms. We can always reduce one of the integrations due to the delta function. It will give you the integral in A perspective, B perspective, etc. Now, once we have a physical state, we can now choose a reference frame and do it by projecting the physical state on the fixed point of the chosen system. It's convenient to choose the origin. The Hamiltonian is also modified by replacing PA with minus PB minus PC due to the momentum constraint. And the evolution is given by standard Schrödinger dynamics, again from the perspective of A in this case. Now, by temporal quantum reference frame, I mean basically Paging-Mutus formalism, which is obtained by using the Wheeler-DeWitt equation with a specific form of the structure of the system, which is divided to clock and the rest of the world. And the total Hamiltonian is a sum of Hamiltonian of the clock and the rest of the world. It can be complicated, doesn't matter now. So time states are defined such as the Hamiltonian of the clock is a translation operator. The time operator for ideal clocks is canonically conjugated to the Hamiltonian of the clock. So basically the last step is to project the Wheeler-DeWitt equation on time states, and that gives you the emergent Schrödinger dynamics from the static picture of the state of the universe, which has no time evolution. Now, combining this idea basically means that our Hilbert space now includes both spatial and temporal degrees of freedom for each subsystem. The physical state should satisfy both constraint total momentum and total Hamiltonian. Now the total Hamiltonian in the initial frame view, in addition to kinetic energies, now includes the energies of the clock, of the clocks. And the physical state obtained the same way as before, applying the constraints on the kinematical state. Again, once we define the physical state, we can obtain perspective by projecting on time states and the origin of the chosen system. So imagine that we have some initial condition in this perspective. We can always find the constrained kinematical function, and that will help us to switch perspectives in the next slide. So we can rewrite the expression for the state in B perspective, and now we have the same kinematical function, but constrained on B. Then we can use the previous one, this one, the initial condition from A perspective, to obtain the way system B sees the environment. So next, I want to concentrate just for the next slide, on the special case of initial condition. So imagine that system A describes the environment in a separable manner. But each degree of freedom is given by its own function, and that means that the constrained kinematical function in B perspective is basically given in a very easy way, just by changing omega B with minus Hamiltonian in its perspective. Okay, so the example I want to solve is, imagine that from A perspective, B particle is a Gaussian, C is a plane wave, and both clocks have a decaying dependence on the energies with the coefficients alpha B and alpha C. Now from my perspective, there's nothing surprising. It's just a spreading Gaussian. But in B perspective, there's some extra term here, which comes from the clock dependence. What is surprising that from when B describes the spatial distribution of A, it actually depends on how A describes the clock of B in its perspective. Okay, you see here this coefficient. So we can take a limit. For example, if this alpha is very low, that means a very flat in energy, very precise in time. So this influence vanishes. So for very definite times, with very definite clocks, there is no such an effect. Okay, so with this example, I show one of the features that I said, so that the shape of the distribution might change while changing reference frames. So it's not symmetric in this sense of shape. Next, I want to talk about more general cases. By general, I mean now we deal with more than 3 systems, general N, and general distributions. So if we want to calculate the expectation value of clock B from a perspective in initial time, initial by parameter TA now, it will have this form of integral. And from such a form, you can always change the constraint. You can put here any constraint you want, from A to N. And that means that you can, this is the form for this initial expectation value. And since so it's anti-symmetric, so the way system A sees clock B in its initial moment is opposite to the way that clock B sees, system B describes clock A. So this is one conclusion. The other conclusion is that you can always add and subtract any pair of derivatives here. That means that this initial expectation values behaves like vectors. So you can see that the initial expectation value of B in A is actually the initial expectation of the way A sees system K plus the way system K looks at clock B. And if you use this property of minus, that means that the way system K describes both these clocks is absolutely equivalent to the way they describe each other. Taking the limit of synchronization, so if the system K sees these two clocks synchronized, that means that it's true for any other system looking at these two clocks, and it's also true about how they see each other. So this property of synchronization or desynchronization is the same for any observer. In the previous slide, I talked about the initial expectation values, and I'll talk about the general T. So the expectation value of clock B from a perspective is its initial expectation value plus the parameter TA in its perspective, and the same for the opposite. So I showed you that they have opposite signs. But I did not show you that the expectation value of T squared is actually the same for both systems when switching perspectives. That means that the sigma of the fuzziness of the clock hand will look the same to them. So if system A sees some sigma of the B of the clock hand, it will be the same when B will look at the clock of system A. So they not necessarily synchronized, but the rate is the same. So for example, taking the derivative of these two expressions with respect to TA and TB, you get 1, and so the rate is the same. So they will not be not synchronized, but the shape of the fuzziness is the same, and the rate is the same. It's not surprising because these clocks do not interact with each other, they do not interact with the special degrees of freedom, they're just independent. Now you can take a limit and ask when these clocks will be perfectly synchronized and show a certain time. So these clocks do not have to be, so these two terms can cancel each other. So as long as these two clocks have the same distribution, they will see each other as synchronized. As for the T squared expectation value, we have here second derivative. So once the dependence of kinematical function on omega is very weak, this term will vanish and you will see very sharp clock hand. now I want to talk about the space expectation values. So the expectation value of particle B in A perspective is the initial expectation value plus the expectation value of the relative velocity times the parameter TA. And the similar result for the when switching reference frames. By relative velocity, I mean P over M. Once you substitute the constraint, it becomes this expression. And of course, not surprising that the same. I mean, the relative velocity between B and B and A is the same in both perspectives. And that's the shift I presented in the first slide. So for the spatial reference frames only, there is no such term. So if system A describes system B plus L, system B will describe A minus L. So this should be 0. In our case, there is a shift, which is the expectation value of relative velocity times TB in A perspective or times TA in B perspective. And that's how it looks. So we calculated the expectation value of XA in B and XB in A. So the delta 1 is basically this expression. For the expectation value of x squared is a little bit more complicated, but what is important that it only depends on the derivatives with respect to omegas. So when the dependence on clock's energy is very weak, these two will vanish and we'll get back the standard description. But in general, that's not the case. So these signals in general are not the same. And this is the deformation of the wave packet. Okay. So they're in general do not share this property of shape and location when switching perspectives. It's faster than I thought. Okay, so we introduced the spatial temporal quantum reference frames, and we showed that even in the case of non-relativistic regime and without any interactions, there still is a very interesting dependence between spatial and temporal distributions while changing the reference frame. So the possible generalizations of this work, for example, we can take interactions into account. The simpler version is take only the spatial interactions. The more interesting will be taking the temporal interactions between the clocks only, or between the temporal and spatial degrees of freedom, or any combination of these things. Another idea is to take into account that the clocks might be not non-ideal, and of course, relativistic scenarios. Taking the, for example, Klein-Gordon constraint instead of Schrödinger picture. So with that, I want to thank you for being in your reference frame.
Any questions? It's kind of good. It's actually our last night.
Yeah, thanks for this very interesting talk. It wasn't clear to me what came from specifically combining spatial and temporal reference frames. So, for example, the synchronization of clocks thing, that's independent of the existence of the. One could do that with. We discussed it before, right? These clocks would exhibit these patterns even in the absence of a temporal or a spatial reference frame as well, right? Do I understand that right?
Yeah.
Right. But then when it came to the spatial part, would that happen by just simply having a spatial reference frame and then imposing the Schrödinger equation without reference to some kind of clock, or is it necessary? Is the existence of the clock system
Systematic information?
Yeah.
Yeah, definitely you need a clock to do that. Yeah. That's because they
Can you
will
maybe elaborate a little bit?
I was trying to avoid the mathematics, but since we have time, okay. So when you have in this expression, this psychomagical, the omega A is replaced by minus the Hamiltonian in A perspective. So when you take any derivative, when you act on this state, both the T operator or X operator, it will act not only on momentum, for example, but also on this Hamiltonian. So it includes both omegas and p's. So you will get extra terms because each subsystem has its own temporal degree of freedom. And it will not be the case with spatial quantum reference frame. So there, the dependence comes from here.
Thanks. Anybody else?
Quick question, since we are here to clarify. When you were looking at states of particles in various frames, including the clock, the states that you were taking, were there, when you write time of TA, is the TA the time of the clock, or the T's and B's were just some particular time parameters that were independent of the clock here, or are these the degrees of freedom of the clock, or is it the parameter here?
Okay, it becomes a parameter in this way. While it's like in regular paging motors. When you take the projection, it becomes a parameter, a regular Schrödinger parameter. But for each reference frame, it will be different. So it's on clock parameter.